So today I'll be discussing the Goddard Shale, and we'll jump right in. So this talk will be pretty straightforward. I'll introduce the material that I'm going to discuss, the methods that I use to get my results. I'll try to synthesize all that together to what I think it means, and then I have a few points I want everyone to walk away with today. Okay. Now, briefly, I want to acknowledge Newfield for sponsoring this project. They gave us the data and the funding. I also want to thank my advisor, Dr. Passion, and my former advisor, Dr. Boardman, who unfortunately passed away during this project, but he was a really great person to work with. So the Goddard Shale is a localized niche shale play in the Anadarko Basin, okay? And the purpose of this project was to develop a depositional model of the Goddard Shale and determine what are the primary controls on reservoir quality. All right. Now, I had two hypotheses that I wanted to test during this project. And the first one being that the Goddard Shale represents depositional environments ranging from shore zone to shelf, and that clay mineralogy is a dominant control on reservoir quality. Now, here we have a basic map of Oklahoma that shows our basins and uplifts, okay? And in the window, we can see northern Stevens County, southern Grady County, part of McLean, and part of Garvin County. Now, this project focuses around a core that was taken from this well here in northern Stevens County that's in the southern part of the Anadarko Basin. Now, the core was taken in a Pennsylvania structure called the Purdy Subbasin, and the basin or the subbasin is bounded by the Golden Trend to the east, the Chitwood structure to the north, the Carter Knox anticline to the west, and the Washita Valley Fault Zone to the south. And I've got some cross sections coming up that'll actually show the structure, the Pennsylvania structure. And I used 20 wells in this project to get a basic geometry of the Goddard in this region. So you can see from the window here, these are our two cross sections. A to A prime, it's going to be running a little more along strike of the subbasin, and then B to B prime, it's going to be running along dip. So in A to A prime, the you don't really see a lot of structure in the subbasin. There's no vertical exaggeration on this cross section. But if we look at B to B prime, we can see the subbasin, the Pennsylvania structure here, really good with the Purdy subbasin. The cross section actually comes on to the Golden Trend anticline, and then it actually enters another little, excuse me, a syncline or subbasin to the northeast. Okay. Now the Goddard Shale is Chesterian. Here we can see it. Chesterian in age, or Subricovian if you're using the European system. And the unit consists of gray to black shale, siltstone, and dolomite lenses. Something I want to point out about the Goddard is that the reservoir facies that we'll be focusing on does not outcrop, it only subcrops. Okay, now the methods for this project was pretty straightforward. I used innovative formation evaluation. I described the core. I used geophysical and petrophysical logs to do analysis on the unit. I used thin sections to look at the petrology of the formation. I used mineralogical and geochem data to further characterize the kerogen, thermal maturity. And then I used an SEM that's located here at OSU to look at some of the fabric and the critters that are in the unit. So here is really the bread and butter of the project, and this is a core that was taken from that well. I've plotted it beside of your triple or your standard triple combo wireline log, and the core was 162 feet in total length. It was able to capture the complete Goddard Shale reservoir, and that is here. And then I divided the core into 4 lithofacies: the Fissile Shale lithofacies, the Swelling Shale lithofacies, the Reservoir Siltstone lithofacies, and then the Dolomite lithofacies. Now, if we zoom out for just a second, we can actually simplify this core into reservoir strata and non-reservoir strata. Okay, so you'll hear me refer to that as we go forward. And then also identified 4 landing zones for horizontal development in this unit, and I'll talk about that a little bit more later on. So the Fissile shale lithofacies, figure A here is a core photo that is showing what this unit typically looks like. It's Fissile shale with horizontal laminae. You can see cracks in the unit here, and these were forming nearly in front of our eyes when we were looking at the core. This is from just the humidity in the atmosphere and desiccation, just breaking this unit down. It's very reactive to water, and it'll almost disaggregate completely if you get it wet, and we learned that the hard way. But figure B is another core photo that is showing a siliceous layer in the unit, and these are common throughout this facies. Figure C is a core photo that is showing dolomitic siltstone with subhorizontal laminae in the unit. And then figure D is another core photo that is showing the abundant disseminated pyrite and marcasite that's in this formation. Okay. Now, figure E is a thin section photomicrograph that is showing irregular silica lenses that I think are agglutinated forams. Figure F is an SEM image that is showing almost textbook framboidal pyrite that we see in this formation. And you can also see desiccation cracks, and you know, you're looking at these on a micro scale, when in the last slide we were seeing them on a macro scale in the core photo. And then you can also see the abundant argillaceous matrix. In this unit, it's almost completely clay. And then figure G, we have another SEM image that is showing quartz grains here. See these throughout amorphous organic matter. You can see the argillaceous matrix and more desiccation cracks. Now going to the next lithofacies, a swelling shale lithofacies. Figure A is a core photo that was taken right at the base of the Fissile shale lithofacies and then the top of the swelling shale lithofacies. And this is a great example of paired pinstripe bedding. Okay, and then figure B is a core photo that is showing silicon-sided rhombohedral blocks that I see in this unit. Figure C is another core photo that is showing silt-filled burrows and dipping laminae. And then figure D is a core photo, or excuse me, a thin section photomicrograph that is showing silty cross laminae. Now, here's the real bread and butter of the project, and this is our reservoir lithofacies. So figure A is a core photo showing a dolomite concretion. Figure B is a core photo that is showing wavy siltstone bedding with ripple cross laminae and clay drapes. Figure C is a core photo showing a lag bed that has more phosphatic material here on the left and fossil fragments, shell fragments here on the right. Figure D is a core photo that is showing heterolithic cross strata with overturned toe sets. And, you know, I thought this was real interesting with the, you know, if you think about the amount of energy that it actually takes to overturn cross-bedded mud, you know, but I'll discuss that a little bit later on. Figure E is a SEM image showing a large phosphate particle that has pellural texture. You can see the argillaceous matrix of the reservoir, and you can also see some of the abundant pyrite that is in this unit. Figure F is an SEM image that is showing round bodies of organic matter. I think these are Tasmanides. You can also see a demasponge spicule that is really well preserved, and then you can also see the quartz-rich framework of this unit. These are all quartz grains through here. So more figures from the reservoir lithofacies. Figure A is a thin section photomicrograph that is showing a textbook example of an agglutinated foram. This is really well preserved. Figure B is a SEM image that is showing a pyritized radiolarian. This is Spulmonaria. You can also see amorphous organic matter in this image as well. And then Figure C is another thin section photomicrograph that's showing a silicified sponge spicule with ferrone and dolomite. And these thin sections were stained with alizarin red and potassium ferrocyanide. Okay, so now we have the Dolomite Lithofacies, and to the right here we have a core photo of the unit showing graded bedding, and then we have dipping laminae and mud chips here at the top of the unit. And then in this image, this is a thin section photomicrograph that is showing the dolomite crystals really well, and also a large pyrite nodule in the middle. Okay. Now, these are same two cross sections that we were looking at before. A to A prime, it's running more along strike, and B to B prime, it's running more along dip. But now we're looking at these in a stratigraphic setting. Okay. So on A to A prime, you can really see with the Springer sands here in the Goddard Reservoir, prograding cliniforms that are coming into the Anadarko and infilling the basin as they advance. Okay. Now I see the basal contact of the reservoir marking a combined low stand and a transgressive surface of erosion. Okay. And I see the intertonguing of the excuse me, the basinal sands defining a prograding high stand. Okay. I guess something's popping up on something with the zoom here. But we can see some of these higher frequency events in the reservoir, and I think these could actually be parasequences that are assignable to Milankovitch cycles. And then something else I want to point out is in cross section B to B prime, it's running more along dip. We don't see the same relationship between the Springer sands and the reservoir that we do between the sands and the reservoir more along the strike cross section. So maybe the sediment is coming in more along strike than dip, but you know, there could be a disconformity in here. There's different hypotheses. Okay, so here is geochem data, and I plotted selected elements against the spectral gamma curve and the resistivity log. And you can see with sulfur is trending about 8 times higher in the reservoir than in non-reservoir strata. Molybdenum is trending quite a bit higher in the reservoir strata than non-reservoir strata. Cobalt is actually trending lower in reservoir strata versus non-reservoir strata. And then nickel is trending higher in reservoir strata versus non-reservoir strata. Thorium is trending lower in reservoir strata than non-reservoir strata. And then uranium is trending quite a bit higher in reservoir versus non-reservoir. I didn't plot the potassium curve. It doesn't really show a difference in the signature between reservoir and non-reservoir, but we can see that there's not really a correlation to the spectral gamma curve, but there are some weak relationships to the resistivity curve. So here are selected minerals that I plotted against the wireline gamma curve and then the wireline resistivity curve as well. And quartz is reading much higher in the reservoir, about 2 times higher and averaging around 56%. Calcite is also reading nearly 2 times higher in the reservoir versus non-reservoir, and that's averaging about 5%. Now, clays is actually reading 2 times higher in the non-reservoir than in reservoir strata. And these next 3 curves are the clay species, but what I want to point out is the mixed illite and smectite curve, which is reading significantly higher in the reservoir strata. And these expandable clays are going to come into play later on. And again, we don't really see much of a relationship to the gamma curve, but we do see some strong correlations to the resistivity curve. Okay, so these are Rock-Eval parameters that I plotted against the gamma curve and the resistivity curve. And TOC in this unit is averaging around 4.5%. Okay, S1 and S2 are both trending very high. in reservoir compared to non-reservoir strata. The hydrogen index is also reading much higher in reservoir versus non-reservoir. The oxygen index is reading much lower in reservoir strata versus non-reservoir strata, so that's a good thing for production. The normalized oil content is trending about 6. And if you want to flip to 19, this is more Rock-Eval data.
Mm-hmm.
Okay, if you want to go to 20, this is a petrophysical model that was built.
Yep.
And then if you want to go to 21, I'll pick up right here. Okay.
So this is the depositional model.
Yeah. So I'll speak about this and maybe the next slide or two, and then that'll actually be the end of the presentation. So hopefully everybody can hear me and see the depositional model. But this is where that I'm really seeing the context of of the data here with the Goddard Shale. So the Fissile Shale lithofacies I see is representing more of a muddy shelf or a lagoonal deposit, and that's going to be the core photo that's on the lower left of the screen. The two core photos that are more in the upper right is going to be the swelling shale lithofacies, and I see this as more of the shoreline deposit. So the picture on the left is actually showing the silicon-sided rhombohedral blocks, and I see those as pedogenic silicon-sides. Okay, so if you can imagine an environment such as the Baltic Sea, that you have these large mud flats and tidal ranges, and if you have these very expandable clays and you're getting the sea coming in or the tide coming in and hydrating these clays, and they're expanding, and then the sea retreating, the tide's retreating, and you're getting the sun that is desiccating and contracting the clays, and you're getting this expanding and contracting, this hydrating and dehydrating. You'll actually develop these rhombohedral blocks. These are pedogenic silicon-sides because they're going through pedogenesis, the formation of soils. The photo just to the right of that, the core photo, is a pinstripe bedding, and that's very indicative of tidal environments. So those two really complement each other on supporting the shoreline. And also in the depositional model, I have the Springer sands that are being transported into the Anadarko, bringing sediment from the highlands. And then the two core photos in kind of the lower right of the slide is going to be for the reservoir lithofacies, and the one to the left being the heterolithic cross beds with overturned toe sets. I see the reservoirs being more of a distal shelf deposit, and if we think about the overturned toe sets, the amount of energy that it takes to overturn cross-bedded mud is quite high. So this really gives us an idea of what the bottom currents are doing in the basin at this time. And then the core photo just to the right of that, showing some of our clay drapes and ripple cross lamina. There is a dynamic environment that's occurring here. And then kind of towards the front of the depositional model and the bottom, you can see the Dolomite Lithofacies is more of a lens that I have there. And I see that as maybe a tempestite deposit or like an internal wave deposit at the top of the picnic line. Okay. And then if we look at the side of the depositional model here, we can see the interfingering of the reservoir strata with the non-reservoir strata. And I think that really gives us an idea of the cyclicity that we're dealing with here, because during the Chester, we're going in a transitional period from ice house to greenhouse, where it's also characterized by high frequency and low amplitude sea level changes. So if you have a shoreline that's constantly migrating, then you're going to have this interbedded between the different depositional environments. So I think that showcases that well. Ming, if we can go to the next slide, which will be 22 with reservoir development. I can get another call here. You can see I see the primary control on the reservoir as clay mineralogy, and then I see identified four target zones for horizontal development in the unit. And we can see those listed here, zone 1, 2, 3, and 4. Zone 3 is the thickest and kind of in the middle of the unit. But if you remember from the cross sections, the unit actually thins as you get to the northeast. And at that time, the whole unit will become the reservoir. I've actually geosteered in this unit before. And if you can, you will porpoise while that you're geosteering, but if you can just stay in the unit, the whole reservoir will be completed whenever they frack the well, because the seals that are overlying and underlying the unit, which also give us an idea of the cyclicity because they repeat, are just world-class frack barriers. Okay, and the resistivity curve again is showing as a great proxy that we can use to identify net pay. We have a lot of variables that trend right with the resistivity curve, such as quartz, TLC, oil saturation, clay content. Those all trend with the resistivity curve. And then this unit is also overpressured. Okay, this is a source rock in the reservoir, and when it's generating in this location, it cannot escape through these seals. This is also a good opportunity to identify that I think that maybe there was a near shore strong halocline that caused your clays to flocculate near shore and precipitate out, which gave an opportunity for the quartz to continue into the basin, which could give you this reservoir strata so close stratigraphically to the non-reservoir strata, this very quartz-rich reservoir versus very clay-rich seals. So I see that as a possibility. And then, if you want to go to the final slide, the conclusions, I'll try to wrap all this up. So do we have the
Yes.
conclusion slide up? Okay,
Yes.
So a few points I want everybody to walk away with today. So the depositional environments of the Goddard Shale range from near shore to distal. I see the Fissile Shale. Lithofacies is more of a muddy lagoonal deposit. The swelling shale lithofacies is more of a shoreline deposit. The reservoir lithofacies as a distal shelf deposit, and then the Dolomite lithofacies is more of a tempestite or an internal wave deposit that could have formed near the top of the pycnocline. Okay, and then I see sea level changes contributing greatly to the facies heterogeneity and the development of numerous parasequences within the unit. I see clay mineralogy as a dominant control for reservoir quality. And then, I really think the resistivity curve is key here, because a simple log resistivity cutoff can be used to map net pay. Quartz, TOC, normalized oil content, several of these important variables all have a positive trend with the resistivity curve. And then inversely, but just as important, the clay volume has a negative trend with the resistivity curve. But again, resistivity is really showing a key to characterize this in the subsurface. And at this time, I'll take any questions.